mind if you're thinking of using machine learning as an analysis tool. So just the structure of the workshop. So the structure of the workshop, we'll first go over some definitions, why you might want to use machine learning, when you might want to use it, and where you can actually implement and build these machine learning models. We'll then go on to preparing and training your machine learning models. So what sort of considerations you need to make when it comes to your data, preparing your data, splitting it into training and testing sets, and also some of the common algorithms you might encounter as well. And then we'll cover evaluating those models. So after you've trained your model, what sort of evaluation metrics do you use to assess how well it's performing? And we'll cover some things like class imbalances and how that might affect which performance metrics you want to use. And then finally, we'll just conclude with some summarizing remarks, which summarize just the key points of the workshop. So to begin with, quantitative medical images are standard components of the clinical workflow, okay? They're of crucial importance to the everyday management of patients, whether that be for diagnosing the presence of disease, whether that be for offering a prognosis for the likely progression of a disease, or for assessing whether a patient has responded to a particular therapy that we've given them. But they're more than just something visual that we can look at. So this has been a theme sort of the day. Medical images are data. They represent specific anatomical and physiological characteristics of our patient. So if we're talking about, for example, a CT image, we're talking about the electron density at that particular point in the patient. If we're talking about a PET image, we're talking about the uptake, physiological uptake of that tracer at that particular location in the patient. And we can sort of utilize this information, analyze it to yield improved patient outcomes. And one of the ways that we can analyze these images is through machine learning. So what is machine learning? Well, first of all, machine learning is a subset of artificial intelligence. Now, AI is a really broad concept, and probably a lot of people in the room have a different idea of what AI is, but essentially it can be boiled down to just the replication of human cognitive abilities with computer algorithms, okay? And machine learning as a subset of AI is simply defined as the learning of mathematical relationships from input data by a computer program that hasn't been explicitly programmed. Okay, so that's what separates sort of machine learning from hard coding solutions to problems. These models automatically learn the solution that you're after. And a great example that everyone's probably familiar with is your spam email filter. So your email providers will have vast data stores of labeled training data consisting of spam emails and non-spam emails, and they use those to train machine learning algorithms that will then, when they're subjected to a new email that you haven't seen before, they'll categorize that new email for you. So that's a common example of a machine learning algorithm. So artificial intelligence, how does it sort of incorporate itself into the clinical workflow? Well, we have a traditional workflow that might proceed something like this. Patient receives their medical imaging scan. That scan is reconstructed, so we can sort of get a visual interpretation of it. A radiologist then interprets that image, and then they'll highlight any anomalies from that image. Okay, and this information will be used by a sort of team of clinical specialists to make a decision on how to proceed with that particular patient. So in a sort of AI augmented workflow, we can proceed something as follows. The first two steps remain the same for the most part. So the patient receives a medical scan, image is reconstructed, although as Brian might cover in his presentation, deep learning algorithms actually can work with sort of raw image data without working with an actual image, but that's out of the scope of this present talk. And then either the image itself or features extracted from that image are run through our artificial intelligence model. And this automatically highlights anomalies for us. So this can give us sort of a number of benefits. Firstly, it can allow us to optimize treatment regimes. Okay, so we can determine what treatment is the best option for that particular patient. And it can also optimize clinical workflows. So for example, one of the things that has come up probably many times today is the burdensome process of manual segmentations. It takes a while to segment images, segmenting what part you're interested in. AI models can perform this in seconds if they're trained correctly. So optimizing workflows is a big part of AI. But I do want to stress the word augmented. So these models certainly aren't going to be replacing humans anytime soon, and you always need an expert there to confirm that the model is outputting exactly what you want it to output. So why might we use machine learning? Well, first of all, When it comes to data, the volumes of medical imaging data in the world is increasing at an enormous rate, okay? And analysing all this data, either by hand or through manual observations, is becoming increasingly unviable. And we know that medical data is a rich source of information that powerful analytical algorithms can exploit to solve difficult clinical problems that we're interested in. So that's one of the reasons. Second reason is computational resources. So in recent decades, there's been a dramatic increase in the sort of availability of high-powered computational infrastructure. And these resources can facilitate the feasibility of implementing machine learning models on not only large-scale data sets, but you can also do this locally. So if you're just training sort of a basic machine learning model, most of that can be done on whatever hardware you have access to at the moment. When you delve into the realm of deep learning, like Brian's going to cover next, that's when you sort of need that more powerful infrastructure to train your models with. And finally, domain expertise. So some clinical problems just are difficult to solve using domain expertise alone. So this is where machine learning algorithms come into their own. They can be really useful as an alternative to crafting complex, handcrafted solutions to particular clinical problems. So where can you build these machine learning models? Well, by far the most popular programming language is Python. So there's lots of open source packages with online tutorials that you can look at. You almost don't have to be a programming expert to get into it at this stage because there's just so much open source material available. And oftentimes you can sort of just copy paste code that's been used for another purpose and you can adapt it to your particular purpose, tweaking a few parameters. And you can use Python. One way you can use Python is by downloading a data science toolkit called Anaconda. So this allows you to write Python code and scripts really easily. This is what I personally use. It can also be downloaded to your local workstation. So this is important if you have ethics restrictions when it comes to your data, okay? So you can't oftentimes upload your medical imaging data or sensitive patient data to cloud-based services to perform analysis, okay? So this is when it becomes important to be able to work on your local workstation. However, there are cloud-based services available, and one of them is Google Collaboratory. So this is an online platform that's made by Google. It allows you to conduct machine learning experiments really easily using Google's processing power. And it's a great way to experiment without having any computational power yourself. But as I said, ethics considerations are important. So any machine learning models that you train using Google Colab, you need to have that data uploaded to your Google Drive, which is obviously a concern if you're working with sensitive patient images or data. And just for anyone who's sort of interested in getting some really basic understanding of what machine learning is and how you can actually sort of write some really basic code yourself, this book here is a really great one to get you started. So it's called Hands-on Machine Learning with Scikit-learn and TensorFlow. It covers everything in a really introductory way. It also has lots of code there that you can copy paste and sort of utilize for your own purposes. So it's a great way to get started. So preparing and training machine learning models. There's a few sort of key questions that you want to ask yourself before you start training any machine learning models. The first of which is, what data do you have access to? And the second is, what problem are you trying to solve? And your answers to these questions are going to determine how you sort of proceed down the machine learning pipeline, okay? So machine learning itself can be sort of partitioned into different subsections. Two of the most prominent subsections are as follows: supervised machine learning. So this is defined as when you have access to the labeled training data that you want to predict, okay? So in this training, this is the most common, and it's also the most important because anyone, probably the majority of you, if not all of you in this room, if you're ever going to use machine learning, this is the type that you'll use because you're going to have access to what you want to predict. So it might be a segmentation, it might be survival for a particular patient, etc. This just means you have access to what you want the model to learn. Unsupervised is when you don't have any labeled data. So you're just working with input data without anything that you want the model to specifically predict. And in this case, you're just looking at hierarchically clustering your data. So the algorithm will sort of extract features from your training instances and cluster them into different categories depending on similarities between those features. But it doesn't necessarily give you a prediction, if that makes sense. So we'll stick with supervised because that's probably what the majority of you are going to be using. This can be further subdivided into the particular task you're looking to achieve. Okay, so you might be, for example, wanting to classify. You might be wanting to use some radiomics features that you've extracted using Nathaniel's great description. to classify whether a particular region of interest is benign or malignant. So that would be a classification problem. Alternatively, you might want to use those features to perform a regression problem where you want to actually predict a numerical output. So it might be you want to predict from this date, how many months do we expect this patient to survive? That would be a regression problem. So let's look at a full sort of image analysis pipeline. First of all, we have our image. So the image is acquired, it's reconstructed, it can be a PET, CT, MRI, etc. We then segment the area of interest. Okay, so the volume that we're interested in, it can be a tumor, it can be a diseased area, it can be a suspected area of disease that you want to classify potentially. It can be any of those things, just whatever you're interested in extracting features from. Then you undergo some of those post-processing techniques that Nathaniel described earlier, so discretization, resampling, and you undertake your feature extraction process. So you extract some histogram features, some shape features, texture, filter-based, etc. Now, before you sort of implement these features into your machine learning algorithm, you have to select which features are going to be the most important. So you can't just put thousands and thousands of features in a predictive model if you're only training on, say, 20 or so patients, because you're going to vastly overfit your training set and your model will not generalize to data that it hasn't seen before. So you select the most pertinent features and you use these features in your machine learning algorithm. So it can be any of the sort of common machine learning algorithms, and this outputs you either a classification. So like I said, you might want to classify a particular area of interest. It can be a risk assessment, or again, it can be a regression problem. So you might want to actually predict how many months from this date a patient's going to survive based on these features that we have. One way you can mitigate the use of handcrafted features is by using deep learning. This is out of the scope of my talk, but Brian is going to discuss this much more in his presentation. So in this sort of scenario, you don't actually have to specify manually what features you want to extract from the image. The network learns the salient ones automatically. And as I said, Brian will cover that in his next one. So what exactly does this machine learning process look like in practice then? So we have our training data, which is consisted of an input, which is what you want the model to learn from, and a label, which is what we want the model to predict. We put our input into the machine learning model. This model gives us a prediction, okay? And then from that, we calculate what's called a cost function. So this cost function tells us how closely the prediction that the model has outputted approximates the ground truth label that we know to be correct. And we use that information to update the weights of our machine learning model in an iterative process that continues until that cost function is minimized. And in the end, what you hopefully end up with is a machine learning model that predicts your label accurately for samples that it hasn't been trained on, because that's the goal. We want it to generalize to previously unseen data. So quickly on data preparation, let's assume we have this data set here, which I've just crafted at random. The problem statement is we want to build a model that predicts, using these features here, the presence or absence of disease in a region of interest, okay? So we'll make some observations about this data set. The first one is that the scale is significantly different, okay? So, age is between 60 and 80. The first radiomics feature doesn't go above 1, etc. Now, for some machine learning algorithms, this is problematic because they'll assign a higher weight to features that have a higher value. And we don't necessarily want to assign a higher weight to something like age, for example, just because it's higher in value. We want the model to work that out for itself. So we scale our data to be between 0 and 1. Secondly, we'll notice that our data also contains some text. So the actual thing that we're trying to predict just says disease or non-disease. So we want to convert those into numbers because machine learning algorithms don't actually work particularly well with text. They work sort of exclusively with numbers. So we end up with our pre-processed data set. And with this pre-processed data set, we actually want to split it, okay? So we don't want to train our machine learning algorithm on the whole data set itself. We want to split it into a training and testing set. The reason for this is that we have to evaluate our model on data that it's never seen before during the training process, okay? We need an independent assessment of how well the model performs. So we can't just train it and then test it on the same data that we've trained it on. That tells us basically nothing about how well it performs. And a model that doesn't generalize is clearly going to be clinically useless. So this is something that we have to do for every training process. There's some considerations you might want to make when splitting your data. The first question you might ask is, well, how much do we sequester away for testing? And there really isn't a correct answer here. Typically an 80-20 split is used, but 70-30, 75-25 are common examples as well. You can perform what's called stratified splitting. So let's assume we have a total data set with the class distribution that you see on the screen there. Okay, so 15% of our examples are diseased, 85% are non-diseased. Stratified splitting is when we are performing the splitting of our data set, we maintain the class distribution of our original data set. Now, this is important if you have a data set with a large class imbalance, which this one is, and also a limited data set, because if you simply randomly split your data set, you might end up with a training set that has limited or even none of the diseased examples. And clearly, that's something that you want to have in the training set. One thing I want to stress as well is patient-level data leakage. So it's crucial that if your data contains multiple instances of a single patient, that you ensure there is no patient-level crossover between your training and your testing set. Okay, this is a form of data leakage, because what that means is that when your model is being tested on that example in the testing set, it's already seen that patient before in the training set. So if you have a data set that does have multiple instances for one particular patient, which is common, you need to make sure that this is done. And I'll just stress as well that in any sort of machine learning task, the underlying characteristics of the population are crucial. So let's say we have these two populations here. Metastatic prostate cancer patients, population 1, localized prostate cancer patients, population 2. If we develop a machine learning model on population 1, we can't use that for predictions in the second population. Okay, it's extremely important that we don't apply these models in populations that haven't been thoroughly tested. Okay, this can lead to erroneous results and bad patient outcomes. So just a few of the common algorithms you might encounter. Logistic regression is one of the most basic. So despite the name, it's actually a linear classification algorithm. And what it does is it computes the weighted sum of input features. So just like a linear regression does with a bias term, and it outputs the logistic of this sum. So it returns you a probability of your particular training instance belonging to the positive class. And you can see that from the graph there, it outputs a value between 0 and 1. The advantages of this are your probabilistic output allows you to choose your own threshold. And we'll get into why that might be important a little bit later. It also has relatively quick training time and it's highly interpretable. So it's just a linear sum of the features that you've calculated. Disadvantages are that if you have a really complex data set and you're using a linear model, you're probably not going to be able to characterize that data set well using a linear model. So you might need to use something more complicated. One of those more complicated algorithms is support vector machines. So these are highly versatile machine learning algorithms, and they're capable of performing either regression or classification. So essentially what this model does, determines the vectors in the multidimensional feature space that best separate your classes of interest. Okay, so that's a bit of a mouthful, but essentially, can you guys see the mouse? Yeah. So the blue class is class 1, the green class is class 2. The support vector machine calculates the vectors indicated by these dotted lines, which best separate these two classes. So that when it's subjected to a training example it's never seen before, or a testing example, you can then separate those classes based on those vectors. Advantages are it's capable of both linear and non-linear classification, as well as doing both regression and classification tasks. Disadvantages are that it's less interpretable than your typical logistic regression model. It's also sensitive to feature scaling. So remember before when I mentioned that scaling your data is important, this is one of those models where that is important. So if we hadn't scaled our data, this would have assigned a higher weight to our age. It's also not feasible for large data sets. So training time increases dramatically when you use it for large data sets. Some other common ones that you might encounter are the decision tree. So in this one, training instances are partitioned at various nodes where each node represents one of your features until a final classification is made at your leash nodes at the end of your decision tree. The advantages to this are it's highly interpretable. So it's simply just thresholding based on the features that you've calculated. It's also insensitive to the scale of your features, but it is prone to overfitting. So the higher the depth of your decision tree, the more likely it is that you're going to overfit your training data and not generalize well to testing data. And some of the most powerful ML algorithms are ensemble methods. So they aggregate predictions from multiple trained classifiers. This reduces your bias. However, they are considered some of the least interpretable. So what this means is they're considered black boxes sometimes, is what they're referred to in the literature. And this is problematic for clinical implementation because it's hard to interpret exactly which features your model is using to make its predictions, okay? So this is just a visual representation of what that looks like. You have your three models, model 1 and model 2 output disease, model 3 outputs non-disease, and you simply have a majority voting mechanism which outputs your final classification. When you're choosing the best model, there's a number of things that are going to go into that choice. The first of all is your data set, and then the advantages and disadvantages of the particular model you're thinking of using, and also the clinical tasks that you want to solve. But I want to stress that it's impossible to know a priori what model is going to perform the best for you. So experimentation is almost always advised when it comes to any machine learning task, basically. So you've trained your machine learning model. How do you actually evaluate its performance? This is where things get a little bit tricky. We use the testing set that we sequestered away before. So the model was only trained on the training set. It's never seen these testing examples before. We use these testing examples to test how well it generalizes. But what metric do we use? That's the question. So let's just say we use something like accuracy. Accuracy, defined as the instances correctly classified, divided by the total instances in your data set. Why might this be a bad metric for us to use? Well, let's go back to the same testing set with the class distribution that we were describing before. We have 15% of our examples as disease, 85% as non-disease. If our trained machine learning model outputs as its predictions, 100% of them non-disease, so it predicts everything to be not that particular disease that we're looking at, we'll get an accuracy of 85%. So clearly, this metric isn't going to suffice if we want to characterize how well our model is performing, particularly with large class imbalances. So accuracy can work if you have equal distributions of the classes, but with large class imbalances, it's almost the worst one you can use. So what should you use instead? Well, you can't really characterize all the performance of your model in a single metric. So it's best to cover all your bases and present as many of the relevant ones as possible. Two of the most relevant ones will be precision and recall, or sensitivity. So these two metrics define how well you're predicting the positive class. In this case, if we keep going with the example that we've been talking about, the presence of the disease, okay? Now, if we go back to our example from before and we calculate these metrics on the model that's outputted 100% of its predictions as non-disease, we have a precision and a recall of both 0% because we didn't get a single true positive. So these metrics tell us a lot better how well the model is performing, or in this case, how poorly the model is performing. There is a trade-off, however, between your precision and your recall, because consider a sort of binary classification model like your logistic regression. This will output a probability of a particular instance belonging to the positive class. However, you can actually choose the threshold that you want to use. So it'll output a number between 0 and 1. If you choose a low threshold for classifying that positive class, you will have less false negatives and more false positives. And in this case, you'd be prioritizing your recall or sensitivity. However, if you have a high threshold for predicting the positive class, in this case, you would expect less false positives and more false negatives, and you can prioritize your precision in this instance. So essentially what this is just trying to say is that you can tailor this to your particular clinical context. Do you want to minimize false positives or minimize false negatives? What sort of error in your models do you want to minimize? Briefly, some more metrics. So specificity is another metric you can use. It tells you how well you're predicting the negative class. And we can actually plot 1 minus the specificity against the sensitivity. And we can take the area under this curve, which some of you might have seen in some of the presentations earlier this morning. And this gives us a standard single metric that we can use to assess how well a classifier is actually performing. So we can use this for our machine learning models. We can also use something called k-fold cross-validation. So cross-validation is a really good way to evaluate the performance of a model. Let's assume we have our full pre-processed data set again, we split this data set into 5 folds. Okay, so the first 4 folds are not used for the testing, and the 5th fold is used for the testing. Okay, so we train 5 different models on each of those, where each fold represents a testing set for each of the models. Okay, we can calculate any metric that we want on each of those 5 trained models, and then we can get an estimate of the performance of our models. So we can get the mean of those metrics, as well as the precision of our metric as well. So we can actually get a standard deviation. So this is a really common way to evaluate the performance of the machine learning model. And I'll just offer some brief concluding remarks before I stop. So medical images are vast stores of data. We can exploit them to solve a myriad of clinical problems. This is really important, and machine learning is a good analysis tool that we can use to help solve some of these clinical problems. There are a large number of possible algorithms you can use, each with their own unique advantages and disadvantages, but experimentation is almost always key when you're choosing one. However, you do have to be careful when you're evaluating these models. There are some things you have to keep in mind. Metrics such as accuracy are almost always going to be uninformative when you're assessing your model's performance. And I just want to finish by saying that these algorithms are not infallible. So there are really important considerations that you need to take before you think of deploying any of these models clinically, okay? Such as the characteristics of the population on which it was trained, whether it's overfitting your training data, etc. So thanks everyone for listening. I'm happy to take any questions that you have. We might have to keep it brief though, because someone is going to be using this room after us. So yeah, we've kind of had to motor through, but yeah, happy to take any questions.